We've talked in the past about how to find the length of a smooth arc from x equals a to x equals b. What we want to do now is talk about that with respect to parametric equations, because remember, parametric equations are used to represent the movement of a particle in two-dimensional space. And therefore, that would mean that the length of the arc would represent the distance traveled by the particle on the interval. So let's just review how we developed the concept of length of arc. Originally, what we did is we broke our curve into n segments. So here's the kth segment, and the horizontal component is the change in x on the kth interval, and this is the change in y on the kth interval. And through Pythagoras, we were able to come up with the length of the kth segment, which is this. We then added up all n segments, so took the sum, and then we made them infinitely small by taking the limit as n approaches infinity to make the individual segments approach the curve. And so we came up with this limit. And through a little bit of manipulation with this limit, let's just look at that. What we did is we can divide top and bottom by change in x. So if I divide by change in x, top and bottom, I leave this one outside, and I can distribute this one into the brackets to look like so. We then have our limit expressed as the limit of a Riemann sum, which is equivalent to this definite integral. So the question is, how does the development of this formula change when we're dealing with parametric equations? So our starting point is still an x and y coordinate, but it's with respect to time. So this is the x coordinate at time a, and the y coordinate at time a. And this is the x coordinate at time b, and the y coordinate at time b. So remember, there's a third variable going on with parametric equations in the background, time. Our position is x and y, two-dimensional movement of a particle, time happening in the background. So the length of this arc will be the distance traveled by the particle. So just to follow through the development again and look at what changes because we're dealing with respect to time, we can set up our distance the same way, add up all our segments, take the limit. Now what we're going to do here is, instead of dividing top and bottom by change in x, we're going to just divide by change in t. And what that's going to do is that's going to change this here. And so we still have the limit of a Riemann sum, but since it's with respect to time now, it means that our formula will be, well, this won't be 1, this will be dx dt as change in t goes to 0, and this will be dy dt. And it's all with respect to t as t goes from a to b. So you can see how the formula has changed a bit now for the length of an arc when we're dealing with parametric equations versus when we're using strictly Cartesian format, x and y. So just to summarize, if we're dealing with parametric equations and a smooth curve between time a and b, then the length of our arc, which represents the distance traveled by the particle on the interval, is represented by this definite integral. Now let's just take this formula one step further. We're going to define L of t to be the arc length of distance traveled by the particle from a to t. So L of t is the definite integral from a to t of our formula above, and I'm just replacing this t with u since I'm using t in a different aspect right here. Okay, but it's the same formula. It's the length of the arc from a to t. And we're going to move towards coming up with the speed of the particle. Remember that speed is defined as the rate of change of distance with respect to time. Alright, so if I take the derivative of this expression, and I can do that through the second fundamental theorem of calculus, I'm going to get a formula for the speed of the particle in two dimensions. So L prime of t, taking the derivative of this, following that through is going to represent this. And so the speed of the particle in 2 dimensions is this formula. The distance traveled by a particle in 2 dimensions is this formula. So let's look at an example here. We have a particle moving along a path according to these parametric equations, which I have graphed here. So there's the motion of a particle from time 0 moving on. And we want to find the speed of the particle at t equals 1. So speed, we know, is this formula. This is speed at time t. So we need the derivatives of x with respect to t, which would be 2, and y with respect to t, which would be this. And so since we want the speed at 1, we're going to plug 1 into our derivatives, square them, and take the square root. So the second one would be 3 over 2, and you can work that out. Now, with respect to using your calculator on these kind of questions, if you have a simple enough expression and an easy derivative to calculate on your own, then obviously just type it in like this and you get the answer nice and quick. If your derivatives happen to be more complex, you can get the calculator to do all the derivative work and calculation from scratch. I don't tend to use this a lot because there's a lot of typing in to do, but let me just show you how this would work. You do the square root of, now to get the derivative of x with respect to t, you would just go to Math, 8, and derivative with respect to t of, this is the x of t equation that I need, the derivative of that. So I can get that by going variables, y variables, parametric, and then x1 of t, which is where I've got that stored. I'm doing the derivative at x equals 1, and then I'm squaring it. And then I got to do the same thing with the y component. At 1, square it. You can see it takes a lot of typing in, but it works. 2.5. To get the distance traveled by the particle, that's the definite integral. Of this. So you could work that out by hand if it's easy enough to work out, or you can enter it on your calculator. So on my calculator, Math 9, from 0 to 4, the square root of, now I could get the calculator, put all the derivative stuff in here as I did before, but since the derivatives are easy, I'll just do them myself. 2 squared plus 1.5 square root of t. Square that piece, just watch your brackets. So 11.518. And we don't have units. If it had been meters, then distance is obviously in meters. Speed would be in meters per time. Let's just suppose that was seconds. And now the last question is displacement. What's the displacement of the particle from 0 to 4? Well, remember, if I go back to my curve, that's just, displacement is just ending position minus beginning position. And since the position is in 2 dimensions, our beginning position would be and our ending position would be and if I look at my parametric equations from above, just copy them down here again. Our starting position would be times 0 would be 0 for the x, 1 for the y, and at 4 we would be at 8, comma, This would be the square root of 4 is 2, cubed is 8, plus 1 is 9. Okay? So to get our displacement, we need the distance here. Not the length of the arc, but just the distance of the line segment between there and there, which we can get through the distance formula or Pythagoras. So that's 8 squared, which is the square root of 128, which is approximately 11.314 meters if the units were meters. And if you look back to our graph, that does make sense. At time 0, we were starting there at 0, 1. At time 4, we were ending there at 8, 9. The distance is the arc length, but the displacement is the line segment joining the two. And so they would be close to one another in value, since the arc only curves a little bit. And so those two answers make sense.